one feature of elements in the group is their order. So let's see what this is. So suppose you have a group G and you have an element G in G. Then you can consider the sequence G squared. By G squared I just mean the element G into G, G cubed, G to the power 4. So this is G into G into G. This is G into G into G 4 times and so on. So that's an infinite sequence of elements in the group G. And there are two cases. Either these are all distinct or not distinct. In the first case, we say that G has infinite order. In the second case, we say G has finite order. Okay, when we have finite order, we can further specify what the order of an element is. So let's just zoom into that case. So suppose G has finite order. Then what do we know? Then we know that G to the K is equal to G to the L for some K not equal to L. And without loss of generality, we can assume that K is strictly less than L. Okay, but we can rewrite this as G of K is equal to G of K, G of L minus K. And then using cancellation, we get that identity is equal to G of L minus K. So there exists an integer r such that G to the power r is the identity. Okay, so in this case we define order of G to be the smallest integer k, let's say r, greater than 0, such that G to the r is equal to identity. And so for example, the simplest example is if you take the identity element of the group itself, then identity to the 1 is itself identity. So this is order 1. But let's look at slightly more interesting cases. Let's take the group G equals Z mod 4Z. Here we're using addition modulo 4 as the group operation. So what are the orders of the elements here? So let's make a little table. We have elements 0, 1, 2, 3, and we can ask what are their orders. So what's the order of 0? Well, 0 is the identity element of this group. We already know that its order is 1. What's the order of 1? So we have to look at 1. Okay, then we have to look at 1 squared, but here we're using the additive notation, so we have to look at 1 plus 1, well that's 2, 1 plus 1 plus 1, that's 3, which is not 0 in Z mod 4, but we take 1 plus 1 plus 1 plus 1, that's 4, which is 0 in the group. So this G to the power 4 is 0, so our order here is 4. Now what do we do with 2? Then 2 has 2 plus 2 is already 0, so here the order is 2, and for 3 we'll have 3 plus 3, which is 6, which is 2 mod 4, 3 plus 3 plus 3, which is 9, which is 1 mod 4, but when you do it 3 times you get 0, 4 times. So this 3 again has order 4. So Z mod 4Z has 4 elements, one of which has order 2, another has order 1, and 2 elements of order 4. Now I'm going to talk about conjugacy of elements in groups. So let G be a group, and given two elements G, G prime in G, we say that G prime is conjugate to G. We'll denote it by the symbol tilde. If there exists U belongs to G, an element U in G, such that G prime is equal to U, G, U inverse. Okay, I claim that this is an equivalence relation. So to check that something is an equivalence relation, we need to check three things: reflexivity, transitivity, and symmetry. So first let's check reflexivity. So we ask, given an element G in G, is it equivalent to itself? Is it conjugate to itself? So G is conjugate to G just because, well, can we find an element U which takes such that U, G, U inverse is equal to G? Yeah, just take U equals identity. Identity G, identity inverse. Well, identity inverse is identity, so this is just equal to G. So this is reflexive. Is it symmetric? So if G prime is conjugate to G, then there exists U in G such that G prime is U, G, U inverse. But we can write this as G is U inverse G prime U, but U is the same as U inverse inverse. So it's symmetric, and to see that G is transitive, suppose we have G prime is U, G, U inverse, and G double prime is U prime, G prime, U prime inverse. Then G double prime is, now we'll substitute for G prime U, G, U inverse, so we get U into U prime, no sorry, U prime into U, G, U inverse U prime inverse, which is the same as U prime U, G, U prime U inverse. So this means that G double prime is conjugate to G. So conjugacy is an equivalence relation. Let's look at the example of the symmetric group. Okay, now to study both order and conjugacy in the symmetric group, we need to understand elements in terms of what is called the cycle decomposition. I'll just explain this by example. So suppose you have a permutation in let's say of 6 letters, W equals 3, 5, 6, 4, 2, 1. So I've written this in one line notation, namely 1 goes to 3, 2 goes to 5, 3 goes to 6, 4 goes to 4, 5 goes to 2, and 6 goes to 1. Now let's just try to visualize this element. So I'll think of the 6 elements as 1, 2, 3, 4, 5, 6, and let's see what W does to these elements. Okay, so W takes 1 to 3. Okay, and it takes 2 to 5. It takes 3 to 6. It takes 4 to 4. It takes 5 to 2. and it takes 6 to 1. So when you draw it like this, a very different understanding of this permutation W emerges. What we see is that there are 3 cycles in W. So we have this 6, 1, 3. Then we have another cycle which is 2 and 5. And finally we have this very small cycle which is just 4 goes to itself. So these are called the cycles of W. And the cycle type of W is the lengths of the cycles of W written in weakly decreasing order. So in this case there are 3 cycles, their sizes are 1, 2 and 3, and we write that in decreasing order, we get 3 to 1. So this is the cycle type of W. Okay, so more generally, given a permutation W, I1, I2, IR is called a cycle of W if W of I1 is I2, W of I2 is I3, and so on. W of I, say R minus 1 is equal to IR, and then W of IR is equal to I1. So what happens is that these elements I1, I2, IR the element W cycles them. Okay, and each permutation W in Sn has a cycle decomposition. Now one thing you can notice that there's some ambiguity in how we write the cycle. We can write this cycle, so the cycles here are 1, 3, 6, 2, 5 and 4. These are the 3 cycles of W. And this cycle can also be written as 3, 6, 1. There's some ambiguity if it's a circular thing where we start. We can start with 3 and say 3 goes to 6, 6 goes to 1, or we can also start with 6 and write 6, 1, 3. Here we can write 5, 2 instead of 2, 5. Okay, so these are called the cycles of W, and this is how we write them down, the cycles. You just write the numbers in the cycles appearing in their sequential order, just starting anywhere in the cycle. So this is called the cycle decomposition of W. Okay. So now let's see how we can read off order and conjugacy from the cycle decomposition of a permutation. So suppose W is a permutation and it has cycle decomposition C1, C2 up to Ck. So it has k cycles, and the length of the cycle, we'll call it R. The number of elements in the cycle is called the length of the cycle. So this is the cycle of W and this length of this cycle is r. Okay, here we have to postulate that these elements are all distinct. It's implicit in this picture, but it's important. So suppose this has cycle decomposition C1, C2, Ck. So the total length of all the cycles will be the n, the set on which, the size of the set on which W is a permutation. Okay. So now you can ask, what is the order of W? Okay, and let's just start with a simpler example. Let's take W to have just a single cycle. So suppose W is the permutation 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6, and 6 goes to 1. Okay, so you can draw this like this. What is the order of this element? So if you look at W squared, well, it'll take 1 goes to 3, right? So this is W, but what is W squared? So let me draw W squared. One goes to 3, 2 goes to 4, 3 goes to 5, 4 goes to 6, 5 goes to 1, and 6 goes to 2. So it doesn't have the same cycle structure. But anyway, we don't really care about the cycle structure of W squared. We just want to know whether W squared is the identity or not. Well, to check that is very easy. W squared of 1 is 3, W cubed of 1 is 4, and so on. W 5 of 1 is 6. So W squared, W cubed, none of these can be the identity element because none of them take 1 to 1. But W6 of 1 is 1. Okay. And you can check that W6 of I is I for all I between 1 and 6. So the order of W is 6. Okay, now let's go back to this element that we were looking at here. It has 3 cycles and I want to know what its order is. So what I know is that on this cycle it will take all the elements back to themselves. So I want to know when is Wk equal to identity. Okay, so what we have is that W cubed will be the identity on this cycle. On this cycle, W squared will be the identity, and here W already is the identity on just the elements of this cycle. So if you want W to be the identity on all the elements of the set 1 to 6, then you need a multiple of 3 and 2. Let me state this a little more precisely. So if I1 IR is a cycle of W, then W to the K IS is equal to IS for all S in 1 to R if and only if K is a multiple of R. Okay, so if W has cycle type, cycle decomposition, C1, C2, Cl, where C1 is length of C1 is, let's say, lambda 1, length of C2 is lambda 2, length of Cl is lambda L, then W raised to K is the identity on the whole, is equal to the identity in Sn if and only if K is divisible by lambda I for all I equals 1 to L. So if you ask what is the least K, the order of W is the minimum K greater than 0 such that lambda I is divisible by K. But this by definition is the LCM of lambda 1, lambda 2, lambda L. So what we have is the following result. Theorem: if W in Sn has cycle type lambda equals lambda 1, lambda 2, lambda L, then the order of W is LCM of lambda 1, lambda 2, lambda L. So coming back to this example here, the order of this element is the LCM of 3, 2 and 1, which is 6. Okay, now let's try to understand conjugacy of elements using cycle type. Okay, so let's consider again our example permutation, which was W equals 3, 5, 6, 4, 2, 1, and I'll draw it. Cycle type: 1 goes to 3, 2 goes to 5, 3 goes to 6, 4 goes to 4, 5 goes to 2, and 6 goes to 1. Okay, and let's try to do some conjugation. So let's take U to be the element, some other permutation. Let's say U is 3, 1, 4, 2, 6, 5. Okay, and what I want to know is what is U, W, U inverse. Okay, so let's look at what happens to U, W, U inverse. Okay, so we need to figure out what it does to various elements of the set 1 to 6. So let's look at what happens when we apply U, W, U inverse to U of 1. Okay, I'm not going to apply it to 1, but I'm going to apply it to U of 1. The reason for this is, well, this is the same as U, then we'll get W, U inverse U of 1, but that's the identity, so you'll get U of W of 1. Okay, similarly U, W, U inverse of U of 2 is U of W2. U, W, U inverse in general of I will be U of Wi. So what we see is that so u of 1 is 3. I'll just rewrite these things in the same shape. So u of 1 is 3, u of 2 is 1, u of 3 is 4, u of 4 is 2, u of 5 6. Then u inverse, it sends u of 1 to u of w of 1. So it sends u of 1 is 3, u of w of 1 is u of 3, which is 4. It sends u of 2, u of 2 is 1, to u of w of 1. So the cycles, which is 5. If you just work this out, you'll see that you get exactly the same pictures, except that I here is replaced by u of I. Okay, so the cycles. So what this equation here means is that if I1, I2, IR is a cycle of W, then UI1, UI2, UIR is a cycle of U inverse. That's exactly what it's saying. Because if I1 goes to I2 under W, then UI1 goes to UI2 under UW inverse. And if I2 goes to I3 under W, then UI2 goes to UI3 under UW inverse, and so on. So what we have is that W and UW inverse have the same cycle time. Conversely, suppose W and W prime have the same cycle time. Then, so let's go back to this example that we had on the previous page. We have the permutation, which our original example, which was W equals 3, 5, 6, 4, 2, 1, and we have another permutation W prime, which is given by 1 goes to 6, 2 goes to 2. I'm talking about this one. 3 goes to 4, 4 goes to 5, 5 goes to 3, and 6 goes to 1. Okay, so this has cycles, as we saw, right? 1, 3, 6, 2, 5, and 4. This has cycles, let's see, 3, 4, 5, so then 1 6, and 2. So I want an element u that takes w to w prime. What I'll simply do is I'll draw u as follows. I will take u to be the element which I will match the cycles of w and w prime. So I'll take this cycle here and match it with this cycle here. So I'll map this element to this, the next element in this cycle to the next element in this cycle. So this is going to be my u, and this element here to this. Then I'll map this element here to this, and I'll map this element here to this, and I'll map this element to this. So my u takes 1 to 3, 2 to 1, 3 to 4, 4 to 2, 5 to 6, and 6 goes to 5. And then manifestly I have w prime is equal to u w u inverse. Okay, this u need not be unique. I could have mapped these cycles slightly different. Instead of taking 1 to 3, I could have taken 1 to, maybe let's just change the mapping on this cycle. So instead of taking 1 to 3, I'll take 1 to 4, I'll take then I have to take 3 to 5, right, because after 1 comes 3, and then I can take 6 to 3. So then I'll get another u, which is 1 goes to 4, 1, 3 and 6 change. So 3 goes to 5 and 6 goes to 3. Then again we have the same equation, that w prime is u w u inverse. Okay, so the theorem that we have is permutations w and w prime have the same, are in the same conjugacy, are conjugate if and only if they have the same cycle time. So example, what are the conjugacy classes? In S5. So we just have to write down all possible cycle types. So the possible cycle types, so you have the identity element, its cycle type is 1, 1, 1, 1, 1. Each element is a singleton cycle. 1 goes to 1, 2 goes to 2, 3 goes to 3. So this consists of the identity element. And the order is 1. You could have something like this, 2, 1, 1, 1. It's yeah, so an example of such an element would be 1, 2 and 3, 4, 5. These are 1 cycles. Sometimes these are omitted because they don't really do anything. Then we have 2, 2, 1. An example of such an element is cycle type. So this column will have examples, and let me write down the order also here. So the order here would be 1, the order here would be 2, 1, 2, 3, 4, 5, the order here would be 2, Then we have 3, 1, 1. You could have a 3 cycle and then 2 1 cycles. The order here is 3. You have 3 2. For example, this, and the order here is 6. And then you could have 4 1, which is 1 2 3 4, and 5. The order here is 4. And then you could have a single 5 cycle. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, and 5 goes to 1. This guy has order of 5. So these are all the conjugacy classes in S5.